All right, take two. I filmed this for an hour and my video just didn't record audio for some reason, which is fun, but let's hope for the best. Welcome back, everybody. Welcome back to the channel. So, today we're going to be talking about the threading system again. So, we're going to be continuing where we left off. So, in the previous episode, I kind of talked about how to create a thread. Now, we're going to talk about how, in general, the threading system works. So if I go to the thread state, we can see here that we have a couple different thread states. And my threading system, just like in Android, is going to have a life cycle. So the life cycle and the way that it works is each thread that's created is going to start out as the created stage. That means that the thread has been born, but it's not technically alive yet, if that makes any sense. And then after that, we have the started state. That's going to be the state that signifies that, yes, based on the software, we have started the thread. So, we spooled up a Win32 thread or a POSIX thread. But at a little bit more of a high level of our threading system, it hasn't been determined to be running yet. So, and there's an important distinction there because that started to running phase is kind of what is a cause for a lot of issues in my threading system. So that's why I have kind of two of those. So after that, we're going to get to the main life cycle of a thread, and a thread is going to consist of two main states, running or suspended. In my language, a thread can be running, obviously that means it's executing some source code, or it can be suspended, meaning that it's put to sleep. A suspended thread is expected to basically be in a sleeping state and be able to be in that sleeping state for an indefinite amount of time. So it conserves energy by actually putting the physical thread to sleep so that other threads can do whatever they need to do. And then, of course, after we get out of there, so typically we'll be bouncing around in the running to suspended. Once we get out of that, then we're at the final stage of a thread's life, which is when it dies. So once the thread is killed, that means that the thread is finished executing or that the thread has been interrupted. It doesn't really matter. Both cases have the same state result. And yeah, so let's actually look back at the source code. So we're going to start out with a couple different functions. So we're going to start out first with the suspend self function. Now, whenever a thread decides to suspend itself, whether it be to another thread telling itself to suspend itself, or a thread just putting its own self to sleep, which you can actually do, a concept of that is called waiting. And basically, what a wait is we're waiting for a signal to be fired or some event to happen to wake us back up, basically. So, those events can span anywhere from our garbage collector telling us to go to sleep all the way up to the high level telling us to go to sleep for whatever reason. A perfect example of this actually is my task scheduling API that basically does this in and of itself. So whenever I need to create a task, I basically execute that task or execute a job, and then that job then runs for X amount of time. And then once that thread is finished with that job, the thread then puts itself to sleep basically and wait for the next job to execute. And then the task scheduler will then wake that thread back up to tell it that, hey, there's another job for you to execute. That's how we're able to basically run multiple jobs on a single thread without having to spool up a new thread for every single job. So in suspending, you want to do two things. So I have a suspended Boolean and I also have a signal of tsig suspend. Now, typically what we want to do when we're handling signals, this is going to be the first example I actually think of me showing you guys how I handle signals in the programming language. And I've mentioned this before, but a signal in short is basically just a way for us to know that something has happened. So all this send signal is going to do is it's not actually really sending a signal in the traditional sense that you may think. It's just either flipping a bit on or off on the actual thread based on, whatever signal we want to enable. So you can see here, this is the source code. You can copy it down. It just does a simple bit shift on whatever bit flag we want to enable. So there's that. And so in this case, we want to consume the bit. So we want to say that yes, we've actually consumed the signal to suspend ourselves, and then we wait. So when it comes to waiting, we use thread self to wait, and we basically want to wait for an indefinite amount of time. So we have this max retries, which is arbitrary. You can put whatever you want. We have a max spin count and a retry count, and we of course set the state of the thread to suspend it. So now we're in the life cycle point where we're actually asleep, and we're going to do a check to see while this thread is suspended. We're going to basically go up into the max retries and then sleep for 5 milliseconds, or you sleep for 5 milliseconds on a POSIX system or a Linux system. I do 5 times 1,000, representing how many microseconds is in 1 millisecond. So we do that way it's the same time on both operating systems. We could also have two other states that represent different things. So we could have a state where the thread is killed in the process, which is entirely possible. So we say we're not suspended anymore and we return out of this function, and we'll eventually handle the thread killed event later on. And then we also check to see if the state is equal to shutting down. So if the VM state or the virtual machine state is shutting down, that means that our platform is now exiting basically. So we want to, obviously say suspended is equal to false and send a signal to kill the thread, and we return. So this is going to send a signal to our thread to basically say die, basically. And if any of you guys are wondering how thread signals are actually processed, like when, at what point does a thread signal, whether it be a suspend signal or a kill signal, get processed, we can look at the opcode, or actually, no, that's a bad example. So I'm going to go to the exec. This is going to be the main loop of our function. Now, let's say we're going to execute some random instruction, right? Let's say we're executing the add instruction. Well, at the end of every single instruction, I have this defined statement called BRH, and that's short for branch to the next instruction. And what we do is I basically increment the program counter, and then I do what's called a branch no increment. What a branch no increment does is it just branches to the next instruction. So in that branch, before I jump to the next instruction, and here I'm jumping to top, this is when I'm doing debugging. Otherwise, I dispatch, which is the most likely thing that I do. You don't need to worry about what this does right now, but as you can see, I have this check where I say has signal, and that then checks to see if this signal flag has a value. And if the signal flag has a value, then we'll check one of the three states. Are we needing to go to sleep? Are we killed, or are we in an exception state? So this is a very quick way for us to check all three of these all at once, because previously in my virtual machine, I would have a check every time to basically check to see if the signal is equal to this value, is the suspended Boolean set to true, or what's the state of the thread, or do a check for whether or not we have, an exception. And that's a lot of work to do on the processing side because most of these signals will never fire for the majority of the execution time of your program. You're not going to be having an exception every 5 milliseconds. You're not going to be killing a thread every second because that just wouldn't work. And you're also not going to be most likely suspending the thread every 5 seconds. So, this is a quick and easy way for us to basically make sure that we handle all of those and also speed up our execution or overall time. So that's a nice way that I do that. So if we go back to where we were, so that's basically all we do for await, and then we set the thread state equal to running. So if, this suspended is set to false, then that means that we're no longer suspended. We're now back running again, and now we're back in the running state of our life cycle. So that's kind of how threads suspend themselves. And let's see, so now we're going to get into starting a thread. So this is the high level version of this function where we start a thread. So if I go to, where is it at? It's in the thread.sharp. We have what's called a native handle. And a native handle basically represents the link between the high level to the low level. And the native handle is going to represent the actual physical thread ID that we generated once we created the thread. And that's how we're going to manipulate it. By starting it, we may be also interrupting threads or whatever. So we pass in that native handle here as the ID of the thread, as well as the stack size. Now, the way that it works With my language, if you pass a stack size of 0, you're going to basically effectively say that I want to get the minimum, or the, not the minimum, but the default stack size that our language is providing. So if you guys remember early on, I talked about how we had an option to basically pick what is the default stack size of our virtual machine. So whatever that value is what we'll use. So what we do is we get the thread and we do a couple of checks here. So obviously, the thread can't be null, right? If we try to get it and it doesn't exist, then that doesn't make any sense. And if the thread is started, that means we also can't restart it again because it's in that starting to running phase. So if that's the case, then we, want to say we can't start it. So we return this result, and it's going to be any one of these results here. So I've talked about this before, but these are various different processing results that I could potentially have when it comes to processing data in our threading system. So there's going to be a few other states. So we also want to make sure that we can't start a running thread and we can't start a terminated thread. Neither of those make sense, so we of course support that. And if stack size, so if we have a stack size, meaning that this value is not equal to 0, we want to check to see if we have a valid stack size. And what that's going to do is pass in the stack size and see if it's greater than or equal to the minimum stack size, which is 50 kilobytes in my example. Again, very arbitrary. You can pick whatever you want. And now we're at the point where we actually want to start the thread. So we're going to start the thread by setting the stack size, the default stack size. So we're going to either check to see if it's not equal to 0. If so, then we want to pass in whatever the stack size that we're providing from the high level. Otherwise, we're going to provide the default stack size, which is created up here, which for me, in my instance, it is 1 megabyte. So, that's what we're going to do. And we want to say we haven't exited, and the state of the thread is thread started. So now we're at the point where the thread is starting, but it hasn't really started running yet. And here's how I basically create it. So here's an example of how we create threads on the Windows operating system. We basically want to just call the createThread function. And as you can see, I have a series of comments here that explain what we're doing. So you want to set the default stack size, the function to the thread caller, the actual thread object, which is the argument that we want to pass to the thread, default creation flags, and I just pass null for the LP thread ID. Now, we're going to have this interpreter thread start function, and this is a function that I created a while ago. But basically, this is going to represent the main loop starting point of every single thread in our programming language. So it's going to be where our interpreter starts running our thread. That's what's called interpreter thread start. And what that's going to be is that's going to be a static Windows dword API or posix void pointer. These are going to represent the return values of the function depending on which operating system we're running on. And then of course, each of those threads are going to take a void pointer as an argument for data that we want to pass to the pointer. So in our instance, we want to actually just pass the thread object to that thread to then set the thread self so that we can then utilize the thread self as a way to access whatever the current thread that we're running in our programming language. So we'll get into this thread start function a little bit later, but that's kind of the general premise of how it works. And then once we start our thread, then we're going to have two checks. So if the thread is equal to null, meaning that the native handle is going to be equal to null, depending on which operating system we're on, then we want to say that we couldn't start the thread because obviously, maybe the user has too many threads active or whatever. Otherwise, we're going to try to wait for the thread. Now, we're going to try to wait as long as possible, but we're not going to wait indefinitely. So what a wait for thread does is its intention is to basically attempt to wait for the thread to start before we start doing other things because there's some synchronization issues when it comes to actually starting a thread. Now, I do have protections at the high level as well for, making sure that we're not accessing or doing stuff on threads that haven't been started yet, but you just want to make sure that you can try to do this at the low level. So what this function does, this is exactly like the wait function that we saw previously. We're going to basically spend for a maximum amount of retries and a maximum amount of spend counts. And if we hit that limit, then we're just going to say max spend give up. So we're just going to give up basically. And that error is, I think, 255. Yeah. So that shows that, obviously this ends. So we're going to be checking to see while the thread state is not equal to running, we'll just be waiting for it basically. Now, if we don't spin out and give up, we're going to just return a result, okay. So that's kind of how it works. And of course, I sleep for like 1 millisecond, depending on the operating system. And yeah, so that's kind of how that works. And for pthread, I kind of do the same thing. I do a different setup for pthreads. So I set up the thread attributes, and then I call pthread create, and I pass in the same data that I passed up here. And if the pthread returned anything other than 0, then that means that it couldn't be started. Otherwise, I wait for the thread. So it's the exact same way. So that's starting a thread, but what about destroying threads? So a thread destruction basically means that we are done with that thread and we no longer need that thread at the high level. So that's basically this function. I actually don't think is used for any practical purposes. I actually don't know if I still need this because it's automatic anyway, but basically what we do is we check to see if the ID is valid by making sure that the current thread is not equal to the ID itself, because threads cannot destroy themselves. That doesn't make any sense. And then we also want to make sure that the ID is not equal to the main thread. We can't destroy the main thread. That's not a legal thing. We return the appropriate result. And then we want to do some other checks. So we want to get the thread and make sure that we actually have a thread to destroy, and that the thread is not equal to a daemon thread. As I mentioned before, daemon threads are special privileged threads that basically signify that the thread can't be tampered with. So once we start a daemon thread, we are basically expecting that thread to be a long-running thread, and we're not going to be able to interrupt that thread or do anything to it. So we return the appropriate result for that, and then we come down here to this destroy function, and we want to just do a few more checks. So we want to see if the state of the thread is either killed or the thread is terminated. If either of those are true, then we want to pop the thread. And what that does is that basically takes a thread ID, and we guard the thread monitor, and we basically just remove it from our, oops, I'm on the wrong function. We get the thread monitor, and then we just want to remove it from the actual thread list of our hash map. So it just removes the value. And once we remove it, then we want to terminate the thread. Now, thread terminations are basically a call to actually destroy the thread in terms of all the assets and memory that the thread actually holds. So whenever it comes to thread termination, we want to guard the mutex. So this is going to be the first example where we're actually going to see the usage of mutex for each individual thread. This allows for proper synchronization. So that way, if multiple threads call this, by the time they get to executing this code, we don't get a double free corruption because we've already freed up the data. So what this is going to do is it's going to be just your run-of-the-mill free function, which we basically just free up all the things in our thread. So depending on whatever your multi-threading platform has, you'll want to free up that data here. And for my instance, I set a couple of states. So I say the thread is killed, it's dead, it's terminated. Then I check to see if we have a data stack, meaning that do we have an actual stack in an internal stack within that thread, and I free up that data stack. Now notice I do not free up the stack pointer and the frame pointer because all they are just references to the data stack. So you don't need to free up those values. And then I free up the call stack, which represents the frame stack of our thread, or the stack for calling functions. So you want to do that. I also free up my random object generator or my random number generator. And I free up a couple of other things, but yeah, so you guys just want to make sure that you do that. Also, if we have our JIT present, then I'm going to check to see if that's not equal to null and delete the JIT. Now notice I have a difference between delete and free. The objects that you use the C++ new operator, you want to call delete, and the objects that you use the malloc operator, you want to call free. So that's very important. Otherwise, you will have memory corruption. So just keep that in mind. So to go back, where were we? I don't remember actually. Oh, we were destroying a thread. So once we terminate our thread, then we free it, of course, and we return a result okay. Otherwise, if neither of these values are true, we cannot destroy the thread because it's not in a proper state for us to be destroying it. So that's how we destroy a thread. Now, what about interrupting threads? So as I've mentioned before, thread interrupts are final. Once you interrupt the thread, there's nothing you can do. Now, I know some of you might be thinking, well, isn't that dangerous, right? Because what if I have a mutex lock on a specific object and that thread just dies instantly in the middle of that mutex lock? Or what if I'm reading or writing to a file and something happens? Well, I do have a plan for fixing that, and I actually am 50% of the way there. Basically, and we'll see kind of how I implement it, so you'll see how you can implement it yourself. But basically what I do is every time a thread exits, I basically want to free up any assets that that thread has available that it is accessing. So even though thread exits or thread interrupts are final, we still have the ability to free up those assets. So I basically release any locks that the thread has, as well as in the future, I'm going to also be closing any file pointers that I may have open that that thread has access to. So just keep that in mind so you don't really have to worry about that. That's a very easy thing to implement in your platform. So we want to make sure that the current thread that we're interrupting isn't ourselves. That doesn't make any sense. Then we do a few other checks. So if we don't have the thread or it's a daemon, obviously you can't interrupt the thread or you can't interrupt the thread that doesn't exist. We also can't have a thread that is terminated because then there's nothing to interrupt. And we have this interrupt function. So what this does is this returns a result. Now, what this function does is it's a bit interesting. So I actually think the Dalvik VM does this as well. Basically, if you interrupt the main thread, that's the same thing as shutting down the entire platform. Otherwise, we're going to actually just administer the interrupt for that specific thread. So if the thread state is equal to thread running, then I do a check to see if we are at the main thread. So if the thread that we're interrupting is the main thread, and that ID is always going to be 0, it's guaranteed. If so, then we shut down the virtual machine. Now, I'm not going to go into this shutdown function. We'll go into that later when we get to the actual virtual machine code. But you want to create this shutdown function, and it basically just does what it does. Shuts down the VM, and then so otherwise, if it's not the main thread, then I actually administer a kill signal to that specific thread. So I say the state is equal to thread killed, and I send a signal to the tsig kill. And that basically is going to enable that flag or that bit, and then, the thread will react accordingly. And notice I do use a mutex here, that's very important. So yeah, and then assuming that, we're inside this if statement, one of these things are gonna be successful and happening, so we just return a result, okay? Otherwise, if we didn't get inside of here, we return, obviously we couldn't interrupt the thread because it's not running. So that's kind of how I do it at the low level. And then I check the result after coming out of it. So if the result is okay and the VM state is not equal to terminated, so if we're good and we're also not shutting down as a result of this happening here, then I want to wait for the thread to exit. So the reason why we want to do this is we don't just want to kill the thread and just be done. We actually want to wait for it to try to exit, and this is always going to happen. So if we send an interrupt signal, we are guaranteed to kill that thread immediately. So this is an indefinite wait that basically waits forever for the thread to exit. Now, based on years of testing my platform, this is a guaranteed thing to happen. So you don't have to worry about, this spinning inside of here indefinitely because of some weird stuff happening. And we just sleep for, 1 millisecond each time. So that's kind of how that works. This is just like the other wait function and the suspend function that we've already seen previously. So there's that, and then we return the result, of course. So that's how we interrupt threads. Now, what about actually suspending a thread at the high level? So again, we're going to be passing down that native handle that I talked about. So as we're creating threads, each thread is going to have its own individual native handle. So if you want to suspend a different thread that maybe was created somewhere else, you could just access that thread object and then, suspend it by passing the native handle. So when we do that, we get the thread and we want to do a couple checks as well. So if the thread doesn't exist or the thread isn't running, we can't suspend it because that's not possible. If the thread's terminated, we also can't suspend it. Now, when we try to suspend the actual thread, there is two potential situations that could happen. Either we could be suspending ourselves, so you could say current thread dot suspend, which is entirely possible. at the high level, or you could just suspend, some other thread that isn't yourself. So if the current thread is the thread that we're trying to suspend, we'll call suspend self, which we've already gone over, which just waits indefinitely until the thread is woken up. Otherwise, if it's not the current thread, then we'll, guard the mutex and we'll send a signal of tsig suspend of 1. So that's how we suspend a thread. And once we actually suspend that thread, we want to just return result OK, because we're just going to assume that, it worked. So that's how we do that. And let's see, so let's go back. So now let's get to unsuspending a thread. So when it comes to unsuspending a thread, there's some weird things with unsuspending threads that I've observed in my multi-threading platform. So it's a little bit different than what you would expect probably. So we get the thread and we want to make sure if the thread exists. So if it doesn't exist, or if we're not waiting and the thread is not equal to suspended, then we basically we can't unsuspend the thread, because that means that the thread isn't going to unsuspend. Now, this wait boolean basically means we want to wait for the thread to suspend. This is due to some very strange and bizarre race conditions with my multi-threading platform. So I have this wait boolean to just wait for the thread to suspend because I have a very fast multi-threading platform. So it's very quick, so that's why I have that. And then of course, if it's terminated as well, we obviously can't unsuspend it, so that doesn't make any sense. So if we're going to wait for the thread to suspend, then we want to basically spin for a certain amount of time, and if we get to the max spin count, or the thread is greater than or equal to suspended, meaning that the thread is suspended or it's killed, then we want to return out of this function. Otherwise, we're going to be waiting while the thread is running and it's not suspended. So every time we're going to spin for about 100, or is this 10 million? Yeah, so we're going to suspend 10 million times waiting for the thread to suspend itself. And if we get to a spin count of, whatever, then we'll try to resuspend it again. And then we'll check to see if the total spin count is greater than the max spin count, which is 25. So we'll basically try to suspend the thread 25 times. And if it doesn't, we'll just give up. So that's that. And then we actually want to unsuspend the thread. So after we've waited for a little bit to try to suspend it, then we will try to unsuspend the thread. And I know this is very weird. I think we'll actually see it when we shut down the multi-threading platform. But there is a valid reason for this. And when we actually unsuspend the thread, we just say suspend is equal to false and return OK, because that's all we do. So that's that value, and yeah. So that's unsuspending threads. Now we can also suspend for a certain amount of milliseconds. So this is very useful. I actually use this in the high level a lot. This allows us to basically make a thread wait for an X amount of time. So we can, suspend for however many milliseconds. So what we do is I get the current thread, I say suspend is equal to true, of course, and I suspend the actual thread. Now this is assumed to be the thread itself, and this is actually unsafe. So I'm actually going to do this. I'm actually going to, and I'm going to guard, G-U-A-R-D, the thread, the mutex of that actual thread. So that way we can basically guard this mutex and set the signal of suspend to 0, and then we just wait for an indefinite amount of time. So we can either wait for, and this is based on my high level API, and this translates down to low level. So if the milliseconds is -1, we wait indefinitely until there is a signal of unsuspend being sent to our thread, or we wait for a specific amount of milliseconds. So this function is exactly like the other indefinite wait function that we saw before. The only difference is that instead of checking for a max retry count, we check for a max mill. So we check to see if, we've extended over the maximum amount of milliseconds that we're supposed to wait for. The way I track this is I get the base time of where we start executing this function. That's going to be how many milliseconds since, January of whatever. You guys know what it is. Since that time, and then we basically get that as the base count, and then we also create a now variable. What I do is I calculate the elapsed time by getting the current mills since, whatever, and then I subtract that from the base time, which is going to give us, because of course time moves forward, the difference of time since we first called this function. And then I'll check to see if the mils, which is what we passed in here, so if we want to wait for 5 milliseconds, is minus the now, which is how much elapsed time there has been since we called the function. If that is greater than 0, that means that we are still waiting for this function to exit. Otherwise, if it's negative, that means that we've passed the elapsed time and it's time to exit. So we're going to basically just spin a bunch of times, and every time when we get into this function here, we're going to sleep for the sleep interval, which is just 1 millisecond. So we're going to sleep for that based on the high and low level. And then after that, we do a couple other checks. So we do the same stuff that we did up here, which is, whether or not it's killed or whether we're shutting down. That's fine and dandy. Then we also want to do an additional check to see if it's negative. So if the elapsed time is less than or equal to 0, we want to say suspended is equal to false and break out of this while loop. And then we're going to set the state to running. So assuming that we break out of this function or this while loop here, we'll set that value. So that's kind of how we suspend for a certain amount of time in our multi-threading platform. And now here's how I join a thread. So when it comes to joining threads, it's just like you pictured. You want to wait for a thread to finish. There are some rules about this. Now, I do a check currently to just make sure that the current thread is not equal to itself. A thread cannot join itself. That doesn't make any sense. I also have a check. Now, I don't have it active right now, but we do also want to check to see if the ID is less than or equal to the JIT thread ID, meaning that we cannot join the JIT thread, the garbage collector thread, or the main thread, because those threads are assumed to never finish. Now, I know the main thread can finish, but that's just a rule that I have. You can't join the main thread, so that's what I do. But obviously, you do not want the user to be able to join the JIT and the garbage collector thread. That's definitely not a good thing. But yeah, so we get the thread, and if the thread doesn't exist, obviously that's an issue, or it's terminated, obviously that's also an issue. Then we just say thread join. So we pass in the threading object. Now, if the thread is started, then we want to basically wait for the thread. Now, again, remember, we do have a timeout, right? So we will eventually give up. So there is entirely possible that we could try to join a thread that still technically hasn't started yet. So we just want to make sure we cover our tracks and still try to wait once more for that thread to start. Eventually we'll give up, but once we get out of that function, or even if we don't call it, if the thread is running or it's suspended, then we theoretically can join that thread, because even though a thread is suspended, it's still in the technically active part of its life cycle, so it's legal for us to join it. So what we do is we just call this wait for single object in Windows and return OK. Otherwise, for posix, I do a pthread join on the actual threading object or the handle of the OS dependent threading pointer. And then if it's not equal to 0, obviously it failed. Otherwise, I return OK. Now, Windows doesn't really have this, so I just wait indefinitely. And then otherwise, if I don't get inside this if statement, I return a result join failed. So that's how I do a basic thread join. Now, when it comes to suspending and waiting for a thread, this is used by my shutdown process, which basically just tries to suspend and wait for a thread to suspend, of course. So we just call these two functions. So we already went over suspend thread. So let's look for wait for thread suspend. What that does, this is just like all of our other wait functions. We just wait for a max amount of spin counts. And if that is elapsed or if the thread is suspended, then we're good to go and we just return out this function. So that's how wait for thread suspend works. And let's see, so there's that. We also have terminate and wait for thread exit. So this is also used by our shutdown procedure for our platform. Basically just terminate the thread and wait for it to exit. So in this one, I basically guard the mutex, set the thread as killed, and kill the thread or send that signal. And once I get out of that scope, I just have an indefinite while loop to make sure that the thread is exited. So while it's not exited, I basically just wait, and now if the thread is exited, obviously I return out this function. Otherwise, if the thread is suspended, which actually does happen, Because my platform is so fast, sometimes weird things happen with synchronization. So if the thread is suspended, I jump back up to the top and kill it again, and then come back down in here and just wait for it to exit, which is totally fine. It works. So that's what I do. And then I sleep for, one, whatever. And then after that, I terminate the thread. So that's actually going to call the thread terminate. You want to make sure the thread is exited before you terminate it, because it's going to be still utilizing the stack. So you don't want to kill it before then, because otherwise you'll get an exception or a seg fault. So that's that function. Let's see what else we have. I think we went over, yeah, we went over wait for thread. Next we have priority setting. So if you guys remember, in my thread state, I also have what's called a thread priority. Now, this is an operating system independent enum, which holds various different values that represent different states of thread priorities in my programming language. So if I go back to, what's it, the threading CPP, what we do is if the thread doesn't exist, or the thread is terminated, or the thread is killed, or the state of the thread is created, but it hasn't been started, then none of those are allowed for us to set the priority. So we can actually set priorities of threads even though we're not inside of that thread specifically, which is really nice. So what you want to do is pass in the thread priority, and pass in the thread object and the priority value, which is going to represent whatever the high level value is. And then I check to see if the thread is not equal to 0, or this should be null. So if the physical thread or the physical handle is not equal to null, then we actually want to execute, the code that's in here. Now, if the priority is equal to the priority, we just return OK, because obviously you can set it multiple times and it doesn't make sense to run any of this code if it already has that value. And what I do is I do a switch for Windows. So I check based on the priority. As you can see, it doesn't match up exactly. So for high, I do priority highest. For norm, I do priority above normal. For low, I do priority lowest. Otherwise, if it's neither of these, I say illegal priority set, because it doesn't match one of my high level or one of my platform independent priority values. Now for POSIX, I'm not going to pretend like I know what the hell's going on. I really don't. I do a bunch of stuff to, I guess, set up um, a, a priority, I guess. And if it's high, I do a thing. If it's low, I do a thing. Otherwise, I do a thing. So I really don't know what this does. I copied this off of Stack Overflow, so it works. So I guess. And then I also do a thing after these if statements. And then I return OK, because obviously, this worked. And that's it. And I'm actually just noticing now that I actually don't set the priorities. So what I'm actually going to do is come down here and say thread priority is equal to priority. So assuming that, obviously we don't have, a invalid priority value, and also assuming we don't have an invalid value here, then I obviously want to set the priority and be done with it. So that's the final thing we want to do there. Otherwise, if we don't get in this if statement, then obviously something went wrong. So that's how we set thread priorities. Now let's get into the closing functions for our multi-threading platform. So basically, we're going to have a kill all, or actually, you know what? I'm going to go to the shutdown, because that's more broad. So when it comes to shutting down the multi-threading platform, we want to do a couple things. So if the thread ID is not equal to illegal thread ID, as we know, that is the default value of thread ID. That this TID function, or this TID field, is the basic field that we use to basically generate thread IDs. So if that's equal to illegal thread ID, which is its default value, then I mean, obviously that means that we don't have a main thread and we haven't even started up the multi-threading platform. So if that's the case, we just ignore it. But if it isn't equal to illegal thread ID, that means we have something to do. So what we do is we want to kill all the threads. Then you want to just get all of the threads individually and free up those pointers. Now, here's something I want to mention. I have this max thread ID field. And the reason why you want to do that is because this is a hash map. And as you know, hash maps are not lists. So we don't know what is the total amount of threads that we could potentially be having in that list, and where the gaps are. Meaning that, let's say we have a thread ID from 0, to, I don't know, 140, right? Well, we don't know if in the middle of that, do we have a 45 ID thread? Do we have a 26 ID thread? We don't know. So all we can do is go up to the maximum value of the max or the last thread ID that we generated and check the entire list to see if we have any threads in that list. And this is going to return a Boolean if we actually find the thing that we're looking for. And if so, that means that we have something to free up. So that's kind of how that works. That's why I kind of do it that way. But yeah, so now let's actually look at how I kill the entire threading platform. So I first guard the thread monitor and I suspend all of the threads. Now what this does is this does what you expect it to do. It suspends all the threads. So I reguard the thread monitor, and this is okay because it's recursive mutex, so we don't have to worry. But basically I go up to the maximum amount of threads that we have, and if obviously we have a thread value and we want to just double check to make sure this thread value is not equal to null, then we want to check to see if the thread's ID is not equal to the current thread self, meaning that we're not going to suspend the current thread that we're in. That's very bad. You don't want to do that. And we also want to check to see if the thread is running. So if the thread is running, we want to suspend the thread and wait for it to suspend. So this calls a suspend and wait function, which suspends it and wait for it to suspend. So there's that. Then we also have, so once we're finished suspending all of our threads, now it's time to kill them. So we go up to our max thread, we get every single thread, we make sure that the thread is not equal to null, and then we want to check to see if we're not in the current thread. We don't want to kill ourselves, we want to kill everyone else. So we basically want to check to see if the thread state is not equal to killed and that the state of the thread is not created, because obviously there's nothing to kill if it isn't alive. So we want to make sure we do that, and then if so, we terminate and wait for a thread exit. So this calls this function, which we've already gone over, which just kills the thread and it keeps killing it until it dies. And so once we do that, then we also want to terminate the thread. So if the thread is not in this state, so if it's not the current thread and the thread is not equal to killed and it's not created, we do this, otherwise we terminate it because it's running. That's that, and let's see. So if I go back, that's how we kill everything, and yeah, that's it. So this represents the shutdown procedure for the multi-threading platform. Let's see, do we have anything else? Nope, that's it. So I guess the last thing we have is createDaemon. This function basically starts a daemon thread, so it's a static int, and we want to pass it a parameter of a thread pointer based on which operating system. So for Windows, we have dword winAPI. For POSIX, I have void pointer, and it's going to be a thread pointer function that's going to represent whatever thread we want to execute at the low level. So this start daemon function is actually used by my system. It's not really used for the high level. And then we pass in the thread pointer of whatever thread we want to access. So in here, what I do is I just do a couple checks. So if the thread isn't a daemon or the thread doesn't exist, we can't do that. If the state of the thread is running, we obviously can't do that. Otherwise, if we get past this, then we set the thread exited to false, and then we assign this to the same stuff that we did in the other start function. But the difference is that instead of passing in the interpreter thread start, I pass in the thread function, which is passed up here. That's that parameter. And for this, I do the same exit procedure. So if we didn't create it, obviously that's an error. Otherwise, we wait for it to start. For POSIX, same thing, same deal. Create the thread, pass in the thread function as the starting point, pass in the actual physical thread object that's going to represent the physical thread that we're executing, and we either, if it failed, say it failed, otherwise we wait for it to start. Now this function is used by both my garbage collectors, so if I go up to the memory and garbage collector, what is it? Is it start? I think. Yeah, startup. So I start a daemon, and for the garbage collector, I pass in the garbage collector thread start, which represents the main loop or the starting point to run the garbage collector. For my JIT, I actually have, let's see, so if I go to my JIT, for build JIT, in here I have a startup, which does the exact same thing. So where's that at? So if I go to here, startup, When I actually create the daemon, I create the daemon and I say git thread start, and that then passes this code here, which again does its own thing. So I just hook in the same technology to my multi-threading platform to allow everything to work. So that's why we have that. And once we do all of that, that's pretty much it. So you pretty much have a fully fledged multi-threading platform. The only thing left that we have to go over is exiting a thread, executing an actual thread, and setting up a thread. And that's basically it. So hope you guys enjoyed the video. I know this was a lot of information, so hopefully I explained it as good as I think I did. And if you guys have any questions, as always, put them in the comment section below, or you can always email me. That is in the description as well. And of course, if you guys would love to help support the channel, you can always head over to the GitHub repository at andrewdevcd/sharp. When you do, definitely watch, start, and fork this repository. That gives this language a lot more visibility and let other developers know this language exists. Also, if you're curious about some of the new things that I'm looking to add later on, you can always head over to the roadmap section. And in here, I write some pretty decent descriptions of various things that I'm looking to add to the language to both improve it or fix bugs and so on and so forth. It's a nice interface so that you can kind of see what I'm doing in real time as the language progresses. Now, I haven't really been busy doing this. I've been trying to fix bugs tirelessly so that way I can continue my side project, but eventually I will start doing things in this actual list here. So hope you guys enjoyed the video. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.